Okay, so chapter 7 is where we're going to begin today. And chapter 7 deals with the different types of chemical reactions. So that's basically the focus of this particular chapter, the types of chemical reactions. And there are four main types of chemical reactions. We have combination, decomposition, single displacement, and double displacement. There's a fifth type which I'm going to discuss later on, but it's not included in this list. And the main reason why is because that type is actually one that overlaps with single displacement reaction, or actually combination reactions. So we're going to discuss that type, and that's combustion reactions, but that's for later on. So we're going to cover that after we have completed a discussion of these types of reactions. So I'm going to start off by discussing combination reactions. In some textbooks, they call this synthesis reactions. And basically, what happens in this type of reaction is that you have two or more reactants combining to form only one product. So in other words, hypothetically speaking, reactant A combining with reactant B to form only one reactant, or one product I should say, which is a combination of those two reactants. All right? And I'm going to show you some examples here. So first example is the reaction of a metal with oxygen to form a metal oxide. There are several examples of this. For example, the reaction between calcium and oxygen to form calcium oxide. The reaction between aluminum and oxygen to form aluminum oxide. So those are two examples. You can also have the reaction between a nonmetal and oxygen to form a nonmetallic oxide, such as sulfur reacting with oxygen to form sulfur dioxide, and nitrogen combining with oxygen to form nitrogen monoxide. All right. You can also have a metal combining with a nonmetal other than oxygen. So for example, potassium reacting with fluorine to form potassium fluoride, and aluminum reacting with chlorine to form aluminum chloride. Okay, you can also have situations where you have a metal oxide combining with water to form a metal hydroxide. For example, sodium oxide reacting with water to form sodium hydroxide, and calcium oxide reacting with water to form calcium hydroxide. You can also have nonmetallic oxides combining with water to form an oxyacid, such as sulfur trioxide plus water to give sulfuric acid, and dinitrogen pentoxide reacting with water to form nitric acid. Okay, so that's combination reaction. Then we have decomposition reactions, and decomposition reactions are basically the opposite of combination, where you have one single reactant that breaks down to form two or more different substances. So hypothetically speaking, if you start off with reactant AB, it can break down to form two products, A and B. All right, so let me just go through some examples here. In some cases, you can heat a metal oxide to form a metal and oxygen. An example is shown here: silver oxide heated to form silver and oxygen. You can also have a situation where a metal oxide is basically decomposed to form a metal oxide and oxygen, such as lead 4 oxide reacting or being heated to form lead 2 oxide and oxygen. You can also have the decomposition of carbonates. One of the products will be carbon dioxide, such as calcium carbonate to form calcium oxide and carbon dioxide. You can also have a hydrogen carbonate being decomposed in a similar fashion, but in this case, it will form a carbonate plus water and carbon dioxide. That's what happens in the case of sodium bicarbonate, I should say. Okay, and then we have some miscellaneous reactions that fall under this category of decomposition, such as the decomposition of hydrogen peroxide and the decomposition of potassium chlorate. All right, so these are all examples of decomposition reactions. Oh, here's another one: the decomposition of sodium nitrate to form sodium nitrite and oxygen. So these are all examples of decomposition reactions. Okay, let's talk about single displacement reactions. Now, when it comes to single displacement reaction, this is what happens. You have an element that reacts with a compound that replaces one of the elements of that compound. So hypothetically speaking, let's say you have A, which is one element reacting with a compound, which is a combination of B and C. Then what happens is that the A replaces one of the B's and ends up being combined with the C's, and you end up with B being displaced, right? So that's what we mean by a single displacement reaction. So one very common example of such a reaction is a reaction with certain active metals and acid, right? And what you'll find is that these metals, when they react with acid, produces hydrogen and a salt, which you can determine the formula of based on the formulas of the reactant. So the example that we're looking at here is the reaction between magnesium and hydrochloric acid. The magnesium displaces the hydrogen of the hydrochloric acid. It ends up being combined with the magnesium, with the chloride over here to form magnesium chloride. And of course, the product here, which is being displaced as well, would be the hydrogen. All right. So the salt here is the magnesium chloride. And as I said before, we can determine the formula of the salt based on the formulas of the reactants. As you can see, the formula of the salt is determined as a result of the magnesium combining with the chloride, excuse me, of the acid. Okay, here's another example. In this case, the reaction here is between the metal aluminum reacting with sulfuric acid to form hydrogen and aluminum sulfate. Again, what is happening here is that the metal is displacing the hydrogen from the acid, and you end up with your products being formed. Again, the aluminum sulfate will be the salt in this reaction. Okay, then we have certain reactions where, again, the metal being active will react with water. This typically happens with very reactive metals like sodium and calcium. When they react with water, the sodium displaces one of the hydrogens from the water to form hydrogen gas and sodium hydroxide. The same thing is happening here with the reaction between calcium and hydrogen, or I should say and water. Again, the calcium is displacing the hydrogen from the water to form hydrogen gas and calcium hydroxide. So in both cases, a metal hydroxide is formed. And if I'm not mistaken, in the case of the reaction between calcium and hydroxide, heat is needed, so a triangle should have been placed here. Sodium is very reactive, so therefore no heat is required for that reaction to take place. Okay, in some cases, you can have a metal reacting with water to form an oxide instead of a hydroxide, such as the reaction between iron and water to form hydrogen and this compound here, which is a combination actually of two forms of iron oxide. In some textbooks, they call this tri-iron tetroxide. But this is basically an example of another example of a single displacement reaction where the iron is displacing the hydrogen and the metal oxide will be formed. This tends to take place where the iron or the metal is not as reactive as in the examples we saw before. Okay, so at this juncture, I want to get into a discussion of what is known as the activity series. And this is basically a series of metals placed in order of reactivity. So this is basically what you see here on your screen. As you can see, potassium is the most reactive element in this series of metals. Now, the utility of this series is that you can predict how certain reactions will take place where these elements are involved. Based on this rule of thumb right here, an atom of element in the activity series will displace an atom of an element below it from one of its compounds, right? So basically, the higher the element is in this activity series, the more likely it will displace a lower one from a compound that the lower one is a part of, all right? So for example, sodium, which is here, will displace all of these elements, any one of these elements from their compounds, all right? So based on this, we can tell whether or not a reaction will take place, such as this reaction right here. This reaction we know will take place because magnesium, if you look at the activity series, magnesium is above lead in the activity series, so therefore magnesium will displace lead, and you're going to end up with these products as a result, all right? So this is another example of a single displacement reaction. So as we can see here, this is where magnesium is, this is where lead is, all right? So because magnesium is above lead, magnesium will displace lead from lead sulfide to form the products shown, all right? So that's very useful in terms of predicting whether or not a reaction will take place, whether or not a particular single displacement reaction will take place. Now here's an example of a reaction that will not take place. The reaction between silver metal and copper 2 chloride, right? That reaction will not take place. Why? Because this is where silver is, right? And this is where copper is, right? Silver is below copper in this series, and therefore silver will not displace copper from the copper 2 chloride, and therefore no reaction will take place. All right? So that's an example of the activity series being used to predict whether or not certain single displacement reaction will take place. Now there's another series which consists of the halogens, the elements in group 7. And basically what you'll find is that the halogen higher in the activity series will displace the halogen that is below it. Now the series is the order as established in group 7. So the order of the series would be fluorine followed by chlorine followed by bromine followed by iodine. All right? So for example, in this case, we know that this reaction will take place because in that group, chlorine is above bromine. So therefore, chlorine will displace bromine to form calcium chloride and bromine as your products. All right? So that reaction will take place, we know. And that's because, as we said before, chlorine is above bromine, all right, in the activity series, in this series. Okay, so the next video we'll be discussing double displacement reactions, all right? So until next time.